Thank you.
Good morning, ladies and gentlemen. Good morning, ladies and gentlemen. We want to welcome each and every one of us here this morning. First of all, start by apologizing for the change of venue and also starting date due to some technical issues. However, we're here and we'll kickstart the program immediately. Yeah, the Applied Radiation and Nuclear Physics Research Group from Bello University, Zaria, Department of Physics, in collaboration with the American Association of Physics Medicine Global Research Mentorship Program, organized this public lecture we're here today for. We have today as our resource persons Professor Ahmadu, AAPM mentor, University of Washington, Seattle, USA. Welcome, a round of applause for her, please. He is also here with our mentee, Mr. Joseph Wishat, also from the same university. Welcome, Joey. Representing the Vice Chancellor here today, we have the Director of the Advancement and International Education, Professor Ahmadu. You're welcome, sir. Our chairman of the event today, we have Professor Rabiu Nasiro, who's the leader of ARPNRG. Also seated here today, we have the Provost of the College of Medical Sciences, Professor Bashir Idris. You're welcome, sir. And of course, we have the Dean of the Physical Sciences here with us today, Professor Abdul Kader Ibrahim. You're welcome, sir. Head of the Department of Physics, Professor Ahmadu. You're also welcome. I want to skip Dr. Yahya Musa, representing the Director of SATS. You're welcome. I won't want to belabor us with too many introductions, so each and every one of us here are welcome to this event so that we could kickstart. A round of applause for everybody, please. We'll be taking opening remarks by the chairman of the occasion, the leader ARPNRG, Professor Rabiu Nasiro. Round of applause for him, please.
Morning. Sorry for the start of the lecture. The Vice Chancellor, presented by the Director, Advancement and International Education, the Provost, College of Medical Sciences, the Dean, Physical Sciences, the Head of the Department of Physics, and the Director of the Center for Energy Research and Training. Members of staff from different units of the university, students, ladies and gentlemen. This lecture, the aim of this lecture or the background where, this lecture is where the lecturers are here actually is as a result of AAPM-GREMP project, which was won by one of our members, Dr. Nasuru Nuruddin Garba, and one of our PhD students. Professor Kalpana is a global mentor in this matter, and she's here to see what we are doing, how we carry out some of these activities, both in the way she was in Abuja, where the data was collected, and she will also visit our hospital at Shika to see our facilities there. And after that, she will go back and make a presentation to the body that awarded the grant. These are the reasons for this project. The student is about to complete his program, and as one of the issues, to be met, for the global mentor to come to the university of the student. So she's here with a mentee who is also a staff in the University of Washington. So our aim as a group, a research group, is to actually extend this beyond this lecture. Our intention is actually to extend it so that there will be collaboration and student and staff exchange with the University of Washington, so that we will have many of our students trained in this field. And I'm sure that if this happens, many of our staff in Shika, who are in charge of radiology department, will have some training, and they will update themselves with the new concepts and new techniques of this CT scan. So our research group covers various areas of radiation application, both the radiation from the nucleus and from the shells. So we are into it, and majorly we are looking at issues that concern us. Some of the problems we are having, currently we are working on a radiation shield from a project we got from Nigerian Research Fund. So we are working on that, and the student is also about to complete his program. So let me welcome the speakers once again, Professor Kalpana Kana, and our mentee, Mr. Joseph Wishart, to this university. Thank you.
Thank you very much for those opening remarks. For the welcome address, we would want to hear from the representative of the Vice Chancellor, Professor Umar Buratai. Director of Advancement and International Education, for his welcome address. A round of applause, please.
Professor Kanal, Mr. Joel Wishart, of the University of Washington, distinguished members of management here present, provosts, deans, and heads of departments in attendance or represented, distinguished members of the university community, ladies and gentlemen. On behalf of the Vice Chancellor, I welcome our distinguished guests from the University of Washington. Your presence here today demonstrates the power of international academic collaboration when the institutions of excellence unite in pursuit of knowledge and human advancement. Today, we celebrate a partnership exemplifying modern higher education, bridging continents, advancing science, and solving real-world problems. Mohammed Shafiu research on local national diagnostic reference levels for CT brain protocol and metastatic prediction models under Professor Ahmadu's mentorship addresses a critical healthcare gap. Establishing local appropriate diagnostic reference levels to enhance patient safety, optimize radiation doses, and improve diagnostic accuracy across the country. Now, on the AAPM-GREMP model, this program is a transformative program that addresses international collaboration through connecting researchers with world-renowned experts and cutting-edge methodologies. Campus engagement as a mentor elevates researchers to global excellence. Locally, relevant research meeting international standards and strengthening institutional research infrastructure. It also creates sustainable long-term partnerships. In this regard, we as Ahmadu University seek to go beyond this program and to expand relationships in many other areas of our endeavor. Among these, we are thinking of agriculture and food security. We are also looking to renewable energy and climate science. We are also interested in public health and infectious diseases. One yesterday I was speaking to about tropical medicine, just to draw her attention. We are also interested in data science and AI. There's also infrastructure and engineering. And last but not least, the humanities are also important, because everything we do is for the human being. So problems of the humanities are underlying all of our efforts. So all of these are some of the areas. You've already explained to us you belong to the hospital, but the university advancement is actually involved in your journey here. And who will I, when you go back, to help translate this message and perhaps help open the doors to our discussions and perhaps mutual collaborations in all of this and many more other areas that may be of interest to us. The value that we are selling in regard to this expanded partnership is the fact that we have qualified researchers across the disciplines that we have mentioned. We also have unique research context in the African context or the American context, which may be different from what you experience in America or other parts. We also have state-of-the-art facilities, and we also have got access to diverse population for our various studies. In this regard, we seek, in the context of partners that have explained, joint research agreements on One, faculty science, faculty student exchange programs. We are also interested in joint research programs. We also are interested in PhD supervision, like mentoring professional field. Now there will be other candidates who would be interested to take up supervision of some of these candidates, and we would also like our staff to be engaged in the supervision of their own students who may be studying something related to tropical or African nature. We are also interested in 12 degree programs. One day yesterday I mentioned to you that in the past we had an agreement with the Central China University where we ran the 3+2. It can be a different model that will work that out. Who will work it out, we're sure that the benefit will be very mutual to both of us. In this regard, I want to conclude this address by extending appreciation to Professor Ghana and Mr. Joseph Wishart for taking the time to travel all the distance and for also preparing this meeting to share with us from their wealth of knowledge. To the participants, I call on all of us to listen attentively and to perhaps be able to take notes and ask questions that will improve our knowledge. On this note, on behalf of the Vice Chancellor again, I welcome you once more and I wish us all happy lecture. Thank you so much.
Thank you very much for that. For the background of the project and introduction of the guest, I would want to call Global Mentor, Dr. N.N. Applause for him, please.
Thank you very much. The chairman of the occasion and leader of ARPNRG group, the Vice Chancellor, ably represented by the Director of Advancement and International Education, the Dean Faculty of Physical Sciences, the representative of the Director of Center and Energy Research, the Provost College of Medical Sciences, College of Medicine, the head of department, eminent professors, colleagues, students, our international invited guest lecturers, ladies and gentlemen, good morning. I'm just to give a brief background of this AAPM-GREMP project. It gives me a great pleasure to briefly share the background of AAPM-GREMP Fellowship Grant 2024-2025, which our team in the Department of Physics, Ahmadu University, Zaria, was privileged to receive. The American Association of Physicists in Medicine Global Research and Education Mentorship Program that promotes mentorship, research, and professional development in medical physics, especially in developing countries. Our fellowships connect Ahmadu University with the University of Washington, presented here by Professor Kalpana Kanal and Mr. Joseph Bishop, representative. The collaboration focuses on strengthening capacity in diagnostic medical physics, particularly in computed tomography, imaging, quality assurance, and education. Through this partnership, we aim to train young medical physicists, advance research, and develop locally relevant resources that will support clinical practice and teaching in Nigeria. The visit by our international collaborators is one of the highlights of the fellowship, a practical step in fulfilling the objective of mentorship, knowledge exchange, and research collaboration. We are grateful to the AAPM for this opportunity, to the university for their commitment, and the University of Washington also for releasing our international collaborators, and also for their commitment, and to the university management of Ahmadu Bello University Zaria for their continued support. The project is more than a grant. It is a bridge of learning, a partnership for growth, and a shared vision for the advancement of medical physics in Nigeria and beyond. Furthermore, the grant was won after a competitive selection process, after which then matchmaking was made, in which we were opportune to be matched with one of the best as medical physics practice is concerned. Professor Kalpana is one of the most renowned medical physicists and is a proud member of AAPM. Because I can vividly remember the time we were doing the matchmaking, I was given a compendium list of AAPM fellows consisting of almost more than 500 fellows. I was asked to select 5 and present to the coordinator, Professor Manju Sharma, which myself and Muhammad Jabiru did so and forwarded. But Professor Sharma said no. She thinks our project deserves the best. And at that particular time, she said Professor Kalpana was on leave, but she waited till when she resumed back and talked to her. Because as far as the project is concerned, we deserve the best. And we are lucky we are given the best. We are very proud. So let me conclude by thanking you all for your attention, and I wish you a very fruitful and insightful lecture. So the next segment is just introduction of our invited guest lecturers. I would just like to take a few minutes to give a brief profile of Prof. Professor Kalpana is a professor and director of the Diagnostic Physics section in the Department of Radiology of the University of Washington, where she has worked since 2000. She is also the program director of the Imaging Physics Residency Program at the University of Washington. Kalpana began her U.S. academic journey in 1989, earning an MS in physics, followed by a PhD in radiological sciences in 1996. She completed her medical physics residency at Mayo Clinic and began her academic career at the University of Minnesota in 1998. In 1999, she was certified by the ABR in Diagnostic Radiological Physics, nationally and internationally recognized for her leadership and scholarship. Prof has served in prominent roles across major professional societies. He is currently a trustee for Diagnostic Medical Physics at the ABR and serves on the campaign board. Her past leadership roles include chair of the ACRCT Dose Index Registry and the AAPM Imaging Physics Curricular Subcommittee. Prof is a fellow of AAPR and the Society for Advanced Body Imaging. She has authored more than 75 peer-reviewed publications and numerous invited presentations worldwide. While her research has long emphasized the clinical and practical aspect of CT imaging, her recent interests include forensic and postmortem CT. Prof is a dedicated mentor and a strong advocate for women in science. Prof continues to inspire and support the next generation in medical physics. And Prof was recently awarded a Lifetime Fellow Achiever Award at the just concluded AAPM Annual General Meeting at Washington, D.C. in August 2025. You are welcome, Prof. The next Prof is Mr. Joseph Richard. Mr. Joseph was a dedicated fellow. He is also one of the mentees of Prof. We worked immensely with him, and he is also a backbone of this project we are completing. Prof and Muhammad Shafiu work hand in hand towards achieving the set objective of our AAPM-GREMP project. Mr. Joseph Richard, you are highly welcome. And after his own also residency program under the supervision of Prof, he was employed as a full-time staff of University of Washington. So we look forward to future collaboration with you as well. Much welcome. So thank you very much. This is my short.
Thank you very much, Dr. Weber. Now we'll be having our first lecture, Introduction to CT Dose Metrics.
I think I'm very sorry, I see one also important personality. Let me use the opportunity to introduce the AAPM mentor, Ahmadu Shehu, who is a PhD student in the Department of Physics, and also his research project toward the award of PhD in radiation biophysics. He is currently awaiting external examination. Ahmadu, you are welcome. For the research project, we collected our data also in collaboration with the National Hospital Abuja, and that is why also a visit is going to be paid to them within the week. Thank you very much.
For our first lecture for today, I would like to invite Mr. Joseph Richard, which, like I said, will be taking us on introduction to CT dose. Round of applause for him as he provides his lecture.
Thank you. To all of you, thank you for such a warm welcome. Dr. Canal and I are thrilled to be here, and it's wonderful to meet new friends, new colleagues. We're just happy to be here. Let's just jump right into it then. Do any of you guys watch Star Wars, or is this completely lost on everybody? Do I have any Star Wars people? Okay, thank you. Yes, thank you. Introduction to CT, and specifically on CT dose and how we measure it and how we talk about it. So I'm calling this Physicists and the Phantom Menace. We measure CT dose in these big acrylic drums that we call phantoms. So that's what I was going for there. But we'll do a little bit of an outline here. I'll give you some background why we should care about CT dose. We'll then jump into dosimetry in general X-ray, and then CT-specific dosimetry, which is going to be an alphabet soup of acronyms, and just briefly where we're heading, which will hopefully lead well into Dr. Canal's lecture. Okay, so given the title of this lecture, and I want this to be sort of interactive, so if you have questions or want to interrupt me, please do. But to start, based on the title of this presentation, does anyone know what is wrong with this picture? And to remind you, we're talking about CT today. And if no one's going to answer, I hope Muhammad can answer this. Is this a CT scanner? This is not a CT scanner. This is actually an MRI scanner. And it's a trick question. MRIs are a little more rare, but you'll know it's an MRI because it has this big vent. And MRIs have really big magnets, and they're filled with liquid helium. And if something goes wrong, you push the quench button, and it immediately expands a bunch of gas and shoots it through this tube. And in the States, you can actually just go buy an MRI of the whole body for $2,500. So if you're ever in the States, it's great. Okay, so the goal of CT is to produce three-dimensional anatomic images of the body where pixel values are showing electron density relative to the water. So this is a CT image that you're probably all familiar with, where the grayscale represents how dense something is relative to water. So all of the middle gray is roughly akin to water. So this is liver, soft tissue, muscle, everything that's brighter, bone, vertebrae, that's denser than water, and you can see even some, this is a contrast enhanced exam, so these areas are actually iodine. And then everything that's dark, these pockets of air in the bowel and outside the body, that's all air, which is less dense than water, as is fat. You'll notice this sort of region of subcutaneous fat is going to be darker than water. And we can reconstruct in 3 dimensions with different views, so you can see a coronal scan here and a sagittal scan here. And for those of you who have not seen a CT scanner, this is what it looks like. This is an example from our trauma hospital in Seattle. And inside the scanning room, you see the table, and this is me setting up an imaging phantom, running some tests on this brand new scanner. And then outside the room is what they call the control room. This is also me, both pictures courtesy of Dr. Canal, constantly taking pictures of me, much to my benefit. And I'm sort of plugging in parameters and telling the system what to do. And this is where the technologists sit so that they aren't getting bombarded with radiation every day. If we take a look sort of under the hood of the scanner, we will see a number of components, 2 of which I want to highlight. We have just the general X-ray tube, which is where we're slamming electrons into a big piece of tungsten and producing X-rays that are then shot down to the other side of the bore through the patient and interact with our X-ray detector. And sort of the modern CT scanner are trying to increase the Z range of these detectors to become bigger and bigger, to cover bigger and bigger portions of anatomy with a single rotation. And if you look at it sort of the other way, so now this is a patient would be laying down like so. You can measure the width of the detector in the Z direction here. And this is sort of showing the beam coming down. And I wanted to highlight the beam width itself, because that's going to become an important topic later on. The beam width can be calculated based on the number of elements we have in the Z direction multiplied by their thickness. And the wider your beam width, the more anatomy you can cover in a single spin. So a lot of our scanners at the University of Washington are 16 centimeters in that direction, which is wide enough to cover a single heart or a single head in one rotation, which is really beneficial. Okay, so the next important concept I wanted to touch on is axial versus helical scanning. So in the old days of CT, sort of the simplest method is known as axial scanning. The way this works is you spin the tube one time and then you move the table in, you spin the tube again, and you sort of stack slices one at a time to the patient. You get a single image here, and you move the table, another image there. This is the old days of CT, and this is why it was often called CAT scanning, computed axial tomography. And this is very slow, right? Because you have to spin the tube and move the patient to cover that whole anatomy. So these days, pretty much everything is helical, where the table is moving and the tube is rotating constantly together. And so you'll end up with detector coverage that looks like one of these 2 scenarios. And the question that you can then ask is, how fast should we move the table? And basically, how far should we stretch that slinky that wraps around the patient? And that question can be answered by the concept of pitch. So the pitch is defined by the table travel per single rotation divided by that active detector width. And so if we have a low pitch scan, that basically means our pitch is less than 1. So for every rotation of the tube, the table has moved less than 1 detector width. And so we've effectively oversampled our data. So this is going to give us a really high quality data set, but of course you're moving the table quite slowly. If, on the other hand, I have a pitch greater than 1, that means I'm moving the table more than 1 detector width per rotation, and I'm going to have undersampling. And so the benefits and drawbacks of each, well, data quality improves on the pitch less than 1, but your speed and efficiency goes down, and sort of the converse is true over here. And of course, in this case, you're giving more dose to the patient than in that case. Okay, so why should we care? Why are we all here? Well, I've splashed this recent paper from the New England Journal of Medicine on projected lifetime cancer risk from CT. This is a really active area of research, and it's kind of a hot button topic. And when papers like this get published, you end up having a massive news cycle outpouring from the New York Times to CNN that basically say, watch out everyone, don't go get CT scans because they're certain to give you cancer. That is certainly not true, and we've had journal clubs about this particular paper and papers like it, and there are flaws in not only the sort of methodology, but also in just going about it this way, because what these papers don't tell you is all of the benefits of CT, right? If we go back 30, 40 years before CT, if you have a pain in your stomach, you're gonna go for exploratory surgery. Nowadays, you can get a quick scan, they can diagnose you with appendicitis, and you're in and out in a single hospital visit. And so these papers really fail to capture that benefit. But at the end of the day, perception affects care. So it's important to discuss these topics in a nuanced scientific way so that we know and are educated. If we look at CT doses worldwide, we actually see that from 2006 to 2016, the average US medical radiation dose decreased quite significantly. And this is actually in a time where CT utilization went up. So the number of procedures is increasing, but the overall dose is decreasing, showing that our CTs are becoming more efficient and we're being more judicious with the way that we use this dose. So key points to think in mind as I continue on here. Radiation is a known carcinogen, but for CT doses, effects are extremely small and become difficult to quantify statistically. CTs are becoming more common, but doses are decreasing. And after an initial jump in CT exposure from like the late 80s, early 90s, overall exposure is now going down. But still, best practices are to optimize CT dose by measuring and modifying our protocols. So now we'll jump into the bulk of the talk, which is on dosimetry itself. And from an elementary perspective, dosimetry starts with air. So if I visualize a box of air molecules here and I have a incident X-rays, what happens is called ionization. And this is literally breaking electrons out of atoms. So I've created now atom ion pairs, and I can collect these liberated electrons, and this is what we call exposure, radiation exposure. And this is the most elementary definition of radiation measurement, and this is what we actually measure. This is charge collected per mass of air. So that's going to be units of coulombs per kilogram for those taking keeping score. And this is given the unit Röntgen, and there's a conversion factor here, but I didn't want to bore you with scientific notation. Exposure is the only thing that we directly measure. The way we do it is using these fancy radiation detectors. This is an ion chamber, and sort of if you flip it head on, it looks something like that, where we have a central electrode, and it's held at a high voltage, and we can then draw those created electrons towards that electrode and measure that charge. We're not actually interested in exposure itself, though. We're more interested in absorbed dose. And so what we want to do is we want to calculate absorbed energy, or deposited energy to be more specific. And this is a two-step process. So first we've ionized those charges, and we now have free electrons in tissue. And those electrons are actually what deposit the energy and give radiation dose. So if I picture a piece of tissue here, and I again have some incident X-rays, those are going to create ionizations. And now I've created electrons, and electrons travel in these very tortuous paths, bashing into stuff, and eventually will slow down and deposit all of their form of heat. But they damage DNA along the way, breaking single and double strands of DNA. So ionization is this process that releases energy in tissue, and this is what we call KERMA, air KERMA, kinetic energy released in matter. I think that one's pretty easy. Collisions are what deposit that energy. So we liberate it and then we absorb it. And so going from KERMA to absorbed dose has this conversion factor. There is an asterisk here in that secondary X-rays can be produced by these electrons, and this is what we call bremsstrahlung, or braking radiation. And oftentimes these photons actually escape the local area in which the original energy was deposited. So you have these electrons going around, sometimes they produce X-rays, sometimes they're depositing energy, and it's the difference between those that gives radiation dose. So KERMA and dose actually both have the same units because they're measuring energy in mass. But like I mentioned, KERMA is the energy released versus dose being the energy absorbed. And so in terms of scientific units, these are joules per kilogram, or what we give the gray. This is the most common dose metric that you'll see in literature. And I think it's helpful to sort of visualize the difference between KERMA and dose. KERMA is the addition of all of those liberated electrons, so those black dots. And then dose is the same thing, but we've subtracted out all the radiation that has escaped secondarily. Does that sort of make sense? And please, again, stop me with questions or comments or crises. Okay, so going into CT dosimetry itself, these are the sort of questions we're interested in asking. And we're going to start with the most simple case. So pretend I have a CT beam, a single beam irradiating my very realistic patient here. And what's going to happen is that radiation, like I said, is going to liberate electrons. That's going to cause secondary photons. And overall, we call this process scatter. And so it's not just the primary radiation that's depositing dose. You also get this penumbra of scatter that goes throughout the body. And so if I were to plot this, it would look something like this, where my nominal beam width from the CT scanner might only be 40 millimeters and has pretty strict cutoff. But I'm going to have dose deposition from the scatter tails that extend pretty far throughout the body. This is the most simple case, but of course in CT we have more complicated situations where we're stacking beams on each other, moving the patient through the scanner. So it's going to look something more like this. And the actual dose that's going to be deposited isn't just a single one of these beams, it's going to be the sum of all of these beams, right? So if I plot the actual summed dose for a number of these, I get what we call the multiple scan average dose, or MSAD. I think it's an unfortunate acronym because it makes you sad. But you can see that the actual summed dose is going to be larger than the peak of each of those because it's like adding those scatter tails to one another. And if I stack enough of these beams together, eventually that dotted line is going to reach a saturation. And it doesn't matter how long the scan is, I'm going to reach an equivalent level because all the scatter from this scan way over here won't reach this scan way over here. And so if I sum it all together, I'm normalized. And this is the basis for CT dosimetry. If I then integrate across that whole multiple scan average dose and normalize by the beam width of my scanner, I get to the primary CT dose metric, what we call the CT dose index, or CTDI. And boring mathematically, it's written something like this, where I'm integrating over theoretically an infinitely long distance, but in practice, of course, it's not going to be infinity. And then I'm normalizing by the thickness of that profile, which I introduced earlier as the number of elements times the thickness. So this is the basis for CT dosimetry. That's the theory. What do we do in practice? Well, these are our CTDI phantoms. We have two of them. They're actually sort of nested right now. So we have a 32 centimeter phantom that's supposed to represent a body. And we can actually take out this inner 16 centimeter phantom, and that's supposed to represent a human head. Doesn't it look like a human head? And then here's our ion chamber, and it turns out all of these CT ion chambers are exactly 100 millimeters long. And there's a very good reason for that. We want to standardize doses that physicists A are measuring in Seattle, as the physicists here are measuring in Nigeria, right? So all of these chambers are going to be 100 millimeters, which gives us then CTDI 100, where instead of integrating over infinity, I'm actually integrating, and that is a typo. That should be negative 50 to positive 50, right? Basically over 100 millimeter length. That would technically be over a 200 millimeter length. So if you're taking notes, that's a typo. Negative 50 to 50, and I'm still normalizing by the beam width. You'll notice that those phantoms have a number of plugs. Where am I putting the chamber when I do this measurement? Well, in the case of the body phantom, of course, the center of the phantom is going to get far less dose than the periphery, just because the photons will be attenuated by the time they get there. And this is actually going to be a discrepant factor of around 2, so the periphery is going to be about double the dose. And if my aim is to sort of take an average dose throughout the phantom, then I'm going to have to weight my measurements in a very specific way. And this brings us to the CTDIW. Hopefully you see the journey that I'm taking you on, sort of getting more and more specific. The CTDIW is going to be 1/3 times the measurement at the center, plus 2/3 of the measurement at the periphery. And when I'm actually measuring this in practice, I can put my chamber at any one of these 4 holes, because I'm going to be doing a full rotation, and it's going to be symmetric about 360 degrees, so it doesn't matter. We always put it at 12 o'clock. And this gives me the average dose throughout a slice of my phantom, which is great. That's sort of the goal of CT dosimetry. But keep in mind, this metric is only defined for axial scanning, right? I mentioned it's just a single spin of the tube. I can't have the table move at all during this process of measurement. But remember, pitch still did have an effect on the dose. So if I harken back to one of those previous slides, you remember it was sort of how a measurement of that slinky, right? That dose slinky, how coiled it was. And this certainly has a big impact on the amount of dose that I'm depositing. So how do I incorporate this into my CT metric, even if I'm only measuring axial scans? Well, you can see that more dose for pitch less than 1, less dose for pitch more than 1. And so this brings us to the final CTDI metric, the CTDI ball. This is what you're going to see in every piece of literature on CT dosimetry ever. It's the CTDIW, which is what I just introduced, divided by the pitch. So now for a scan with a pitch less than 1, of course my dose is going to go up as measured by the CTDI ball. So if you remember one thing from today, the CTDI ball is the average dose to one of these phantoms, either a 16 or 32 centimeter phantom, and it is not the dose to a patient. Okay, this is a pretty classic physicist question you might see on an exam if you continue in medical physics. The CTDI ball is not a patient-specific metric. So, what's one issue with CTDI? Well, if I scan 2 patients here, does anyone have an idea which one would have a larger CTDI ball? And this is maybe a little bit of a trick question. Let's say patient on the left, raise your hand if you think patient on the left has a larger CTDI ball. Okay, I see a few hands. What about patient on the right? Okay, who thinks they have the same CT eyeball? Okay, it turns out they do have the same CTD eyeball because the average dose throughout one slice is going to be the same, assuming that the tube output is the same. But clearly, the reason I had people raising hands for number one is because they got more radiation overall. So how do we quantify that? Well, let's just say that the CTD eyeball for this case was 10 milligray for both of them. But the patient on the left was scanned with 100 centimeter scan length, and the patient on the right with 50 centimeter scan length. I'm gonna, yeah. All right, yeah, so the way that we account for these two differences is with a dose length product. And this is the second of the sort of big two dose metrics in CT. And the DLP is the CTD eyeball multiplied by the scan length. Quite simple, dose, length, product. Multiply your dose by your length. And so here, the way that I sort of account for these differences is with the DLP. Patient on the left is going to have 1,000 milligray centimeters. Patient on the right is going to have 500. So even though they have the same average dose throughout a slice, the total radiation that they receive is far different. And it turns out that the dose length product, as you might assume, quantifies the total energy deposition of the scan. And oftentimes we can sum multiple radiations of the same patient and give like a total DLP to understand the total amount of radiation that they received. And you can then use the DLP to calculate what we call the effective dose. The effective dose quantifies sort of the basic radiation risk. And these factors are used for different scans of different types. These are published by the American Association of Physicists in Medicine back in 2008. So for every scan that we perform in a hospital, we actually get the CTD eyeball and the DLP displayed in what we call the dose report. And these are monitored for every patient that comes through our hospital. We can sort of aggregate the data and look at different metrics based on patient size, et cetera. And you'll notice there are a couple other things in this dose report. So what are these things? And also, what's this? Does anybody know what the KB and MA are? I assume sort of those with radiography knowledge. Yeah, great, awesome. Exposure factors, you got it. So KB and MA, or effective mass, is what we talk about in CT. That quantifies the tube output. Yeah, those are the technique parameters. Great. Okay, so I'm going to give you another problem. First of all, is our phantom the same as a patient? No, phantoms are made of plastic. People are made of a lot of other stuff. Another problem, what if we have patients of different sizes, right? I just told you that the CTDI measures the dose to a phantom. So if I scanned all three of these patients with the same parameters, they're going to have the same CTDI ball, but clearly the radiation measurements are going to be different, right? I'd rather be the larger patient because I'm going to attenuate the photons more. So that gives us this new issue, which we solve with these two parameters that you saw in the dose report. The first of which is the size-specific dose estimate, or SSD. And this is going to be correcting for patient size. So it's going to multiply this F factor by the CTDI ball. And the F factor of how to obtain it comes from AAPM task group report number 204. And specifically, we model patient size in this exponential manner. You can see the normalized dose coefficient on the y-axis. That's our F factor as a function of patient size on the x-axis. I think it's getting cut off a little bit there, but that's on the x-axis is what's known as the effective diameter. And what I'm attempting to show here, I think, yeah, the screen is cutting off a little bit, but for a normalized dose coefficient of 1, the patient size is 32 centimeters, which is the size of our phantom, right? So if you are the right size relative to the phantom we use to measure these things, then your CTDI effectively is your SSD. But if we look at an example of a patient scan here, I've just pulled up an image in our DICOM viewer, and I've measured the distance across the patient and anterior to posterior, so lateral and AP. And if I multiply those two numbers together and take the square root, that gives me the what we call effective diameter. And I can use this with the fitted parameters from AAPM report 204 and get a normalized dose coefficient to multiply by the CTDI and correct. In practice, the effective diameter is the diameter of a circle with equal area to the patient of interest. So this patient and that circle have the same area, so I've calculated the effective diameter. You'll also see the term water equivalent diameter thrown around. This is sort of a newer iteration of the effective diameter. It has a more complicated mathematical expression. Similarly, for a patient here, I can draw a region around their entire body and take the mean CT number. So that's going to be right here, 7.47, and plug it into that equation along with the area of the patient. And that's going to give me a circle of water with an equal attenuation to this patient. And this is more accurate than effective diameter because you can see here, this patient actually has more gas in their system. And so that's going to be lower attenuation. So even though they might have a big cross-sectional area, the attenuation properties of their body are going to be less than a patient with more bone or more soft tissue in that region. Between the effective diameter and the water equivalent diameter, we only see about a 10% difference in dose calculations, but just know the water equivalent diameter is going to be more accurate. All right, wrapping up here with a summary. I've sort of brought you on a journey. We started with exposure. This is the one thing we actually measure. It's ionized air molecules. We collect those ions and we measure the charge. That brought us to the idea of CTDI, the CT dose index in its most basic form, is integrating over a z-axis and normalizing by the beam width. That brought us to the weighted CTDI, where I took 1/3 of the central measurement plus 2/3 of the peripheral measurement because the center is going to get less dose. And then that took us finally to our final product here, the CTDI ball, where I normalized by the pitch. Now that we're here, this is sort of bringing me to the future outlook and sort of more advanced things to think about. This is the average dose to a phantom, 32 or 16 centimeters. And this is the metric we can use for research to compare vendors, different protocols, look at dosimetry, sort of make sure all of our protocols are outputting the same amount, even for different vendors. So this is our grand unifier and sort of a helpful research metric. Once we're here, we can also continue on to the dose length product, multiply by scan length, and then finally to effective dose, multiplying by the K factor. Once we're here, we can quantify total radiation detriment. And this is also another sort of future-looking idea where you can do more advanced research looking at cancer risks and other sort of bigger picture things that normalize between patients. I can also go this other route of higher specificity towards the size-specific dose estimate using those F factors and equivalent diameters. These correct for patient size, and this is even further sort of inspiration for research projects. Modern CT scanners modulate the current at each Z location. So you might actually produce a size-specific dose estimate for every slice of your image. That's sort of a nuanced topic, and that brings you maybe to a maximum SSDE versus a mean SSDE throughout the whole body, and just, yeah, another future outlook. I would happily take any questions. This served as a sort of your primer for CT dose, and Dr. Canal is going to talk about sort of establishing then more average metrics and moving on to bigger research, but I'll happily take any questions now. Oh, I think we're going to hold questions until the very end. So apologies, but we'll get to your question.
Thank you very much for that presentation. Like he said, we take questions after Professor Khanna's presentation.
Thank you. Let me just pull up my presentation. All right, good morning, still morning. First of all, how much time check? How much time do I have? 11:40.
Yes.
1 hour for both my talks.
Yes.
Okay, I'll do my best. All right, good morning, everyone. I am Kalpana Nal. I'm a medical physicist from University of Washington in Seattle. Everyone can hear me okay? All right, excellent. All right, I'm going to build on what Joey introduced to you, the CT dose metrics and how you establish diagnostic reference levels. So why do you want to do that, right? How do you know how much dose you're giving to a patient, how much radiation dose you're giving to a patient? So you need to establish reference levels to ensure you're not overdosing your patients. So we'll talk a little bit about diagnostic reference levels. We'll discuss the American College of Radiology benchmarks for common adult and pediatric CT exams in the United States, and how we can use those by facilities to compare their doses to the ACR benchmarks, which is what Mohammed has been doing for his project. All right, so my outline today is, first of all, why is CT dose of concern? Joey mentioned a couple of slides on that. I'm going to skip the CT dose metrics, just kind of summarize what Joey mentioned. We'll discuss what DRLs and achievable doses are. We'll discuss a little bit about the American College of Radiology CT Dose Index Registry, and then discuss establishing the reference levels for both adults and pediatric patients, and then how do you use it in the hospital. So first of all, why is CT dose of concern? This graph is a little outdated, but in the United States, we use CT a lot. I don't know about Nigeria, but in US, everyone is getting a CT. So we're doing annually about 80 million exams, which is a lot of CTs. That means we're giving a lot of dose to our patients. And sometimes if you're not paying attention, you might harm your patients. So this is a case, you can see over here on the head, a little band where the patient has lost their hair, both this patient as well as this patient. And that happened because the parameters on the CT was set so high that it surpassed the threshold of causing hair loss. Now, this is not common, but it can happen. This was probably about 10, 15, 20 years ago. And then this article over here shows this little child who had fallen and gone to get a head CT. And the yeah, you agree with me what I'm saying? The technologist didn't understand what was going on with the scanner, kept scanning the baby, and the baby developed skin erythema because they got so much dose. So these are the reasons why CT is of concern. If you do not use it well, then you could potentially harm the patient. So Joey already talked about CT dose metrics. To remind you, he discussed CTDI, dose length product. He discussed the two phantom sizes, as well as this size-specific dose estimate. So I'm going to skip that. So let's go directly and talk about diagnostic reference levels. So what is a diagnostic reference level? They're typically set at the 75th percentile of the dose distribution from a survey conducted across a wide user base. So if I take a hospital here in Nigeria, and I take several hospitals, look at the radiation dose for a protocol, and then look at the 75th percentile, that will be where I would establish my diagnostic reference level. Then they are an investigational level. It's basically a level at which you start investigating, why is my dose so high at my particular hospital? It identifies exams where levels of patient dose are unusually high. And the overriding clinical objective here is you want to achieve acceptable image quality or adequate diagnostic information consistent with the medical imaging task. I'm just curious, any radiologists in the audience? Technologists? All right. So there are people who have operate CT scanners? Okay, excellent. All right, so as you all know, when you're operating a CT scanner, you want to get good images, but at an acceptable radiation dose. The other parameter of importance is something called achievable dose, and that can be used with a diagnostic reference level to give you the best image quality and set your dose which is acceptable. And this achievable dose is typically set at the 50th percentile. Remember, DRL is 75th percentile, this is 50th percentile. And this is basically saying that half of the facilities are producing images at lower doses and half are using higher doses. So for your hospital, you want to try and be closer to the 50th percentile, the average dose. If you get too high to the 75th percentile or exceed it, that's when you start investigating why your doses are higher. So this graph over here just shows you both the achievable doses as well as the diagnostic reference level. So you want to be somewhere in this area for a majority of your patients. You want to ensure your image quality is appropriate depending on the diagnostic question you're asking, and your optimization must balance image quality and dose. And for CT, all the parameters that Joey mentioned, like CTDI, wall, DLP, and size-specific dose estimates is what you are going to monitor to make sure your doses are reasonable. So how do you determine DRL, which is what Mohammed has been doing? You could come and give this talk, Mohammed. You basically look at your patient dose population. So the hospital in Abuja is called National Hospital. Okay. So that's the hospital where he had all the patient information. You collect your data for your dose, and you establish the diagnostic reference levels. Now, typically you don't do that only for one hospital, but that's where he started. The goal for Mohammed is to do several hospitals, and if possible, actually even all across Nigeria, so that you can establish diagnostic reference levels for the country, like we have done in the US. So you collect data, you compare the data, and you then establish your 75th percentile and your 50th percentile. If your doses are typically higher, then you have to go work on your scan parameters for CT, reduce it, figure out why you're higher in dose, and you keep iterative process every few years to make sure you are optimizing your dose. So the process takes time, and then once you establish it, unless you have a lot of changes in your parameters, you could probably use that for 2 to 3 years. Again, after 2 to 3 years, you want to do this. But in practice, we do this all the time, at least in the United States. You are monitoring your dose all the time to make sure you are not overdosing your patients. So now I'm going to talk about our reference levels and how we set it. So I volunteer for the American College of Radiology, and they have a dose registry. And what does that mean? So the dose registry is basically a tool for quality improvement so that facilities can review your protocols and make sure you're doing okay compared to another hospital. So if you don't have in your hospital a dose monitoring program, you can send all your dose metrics that were defined, information to the registry, and it will compare your dose to other hospitals that are similar to your size, similar type of hospitals, and you'll get a report, and that'll show you how you're doing compared to the other hospitals. The Dose Index Registry was launched about 13 years ago in the United States. You can see here in this figure, the CT scanner will send the dose data to some kind of server at your facility, and that automatically will give you your DRLs and achievable dose reports, and then you can compare that to other hospitals. So here is an example. You can see here. Okay, I think this arrow is not really showing up there, but you can see here that this red line is your median, whichever hospital you are in, and it gives you the whole range from 25th percentile to 75th percentile, and you want to be close to this median. You want to be closer to the median, but between the median and the 75th percentile. And the graphs on the right show you the CTDI for a bunch of exams and how your doses. In one snapshot, you can see how your doses, and if you are close, your red line is close to the middle, that means you're doing well. If your red line is over the 75th percentile, that means your doses are too high. So we published this paper almost now 10 years ago, 2017. We looked at the top 10 adult CT exams in the United States, and we published this data. So now when Mohammed in Nigeria is collecting data, he can compare the dose from exams over here to this paper and see how the hospital in Nigeria, the doses compare to the hospitals in the United States. So that's why we do these kind of studies. So we have established reference levels which we can compare our dose to. So in this study, we looked at the 10 most commonly performed adult CT head, neck, body exams from about 600 facilities. We analyzed those. For head, we use lateral thickness as an indicator of size. And for neck and body exams, we use water equivalent diameter, which Joey mentioned a little while ago. And we looked at about 1.3 million exams. 1.3 million exams, right? When you're establishing benchmarks, you don't look at 5 exams or 10 exams or 100 exams. You look at a lot of exams to make sure your statistics is solid. That's why right now, Mohammed cannot publish a paper based on one hospital. That would be local DRS. You want to look at a bunch of hospitals, get your data so that it's solid statistics. So we looked at 1.3 million exams and we established the median achievable dose. Remember that was 50th percentile, and the mean, the 25th and the 75th percentiles for the dose metrics discussed previously. And we compared this to DRLs from 8 other countries, and all statistical analysis was performed using SAS software. So this table over here shows you the top 10 exams that we use, and you can see here that about most common 44.8% are abdomen pelvis exams in the United States. followed by about 25% chest, and about 10% neck and spine, and 17% head, and some others, but that all comes out to 100%. And this is what we plotted. This shows you the head exam, routine head exam, CTDI is tired. CTDI wall is a function of lateral thickness. So your head thickness going left to right, lateral thickness. The blue is achievable dose, 50th percentile. Red is diagnostic reference level, 75th percentile. And this is what we established for the different head sizes. And the one on the right shows you the DLP. And so on. We did other exams like chest, abdomen, pelvis, as well as the size-specific dose estimate. So as Joey showed, you might give the same dose to two people who might weigh 200 pounds versus 100 pounds. And so the size-specific dose estimate was very important to get a true feeling for the dose given. So the metrics that we established was for head, achievable dose 49, DRLF 57. What does that mean? That means if your hospital for a routine head exam gives for CT anywhere between 49 and 57 milligray for one head exam, you agree with what we established. But if your hospital, your dose, your AD is 60, and your DRL is 75, that means you are giving higher dose compared to the 1.3 million exams in the United States. So that's how you would look at the data. And similarly, we have other metrics, DRLs and AD for other body parts. So that was all adult head CT. That was the first paper we did, and it was the first paper of its kind in the United States. We never had so much data and looked at dose for such a large varying sites. A lot of those hospitals also were grouped, like outpatient or trauma or children's and so on. Then we decided, everyone started saying, okay, now you have adult data, how about pediatric data? So we started looking at that, and we published this paper in 2021. And that looks at the top 10 pediatric exams. I don't know how much here in Nigeria you do CTs on peds patients, but in America, you do a lot of CT. So this shows you, again, some data from the paper. I don't expect you to read it all, but let me just point out some of the highlights. So the one on the top shows you, for adult, I told you we did 1.3 million exams. For children, because we don't do as much as adults, we do children, not as much. We did 1.5, but instead of 3 years, it took us 5 years to get 1.5 million exams. And these are the exams that we looked at. The top table over there shows you the distribution of doing pediatric exams across different types of clinics. So you have academic hospital like University of Washington. You have community hospital somewhere in the city. You could have a children's hospital and so on. And you can see here that most of the imaging is not done at this children's hospital. It's done more in a community hospital, which is interesting, right? It's not a specialized children's hospital. In our age group, you can see we didn't have a lot of data for the younger kids. We had more data for the 15 to 18-year-olds. And then the examination volume shows you that majority of the scanning, 8.1%, is done in hospitals where they do less than 10 exams per month. So the less exams you do for a particular population, the more you need to make sure your protocols are optimized, because you're not doing that many exams. And that's what this showed us, that we need to pay attention to the community hospitals that were doing most of our pediatric exams. And then here's the data. Let's just look at head, the top table over there. It shows you the dose as a function of age. So 0 to 1-year-old, 1 to 2-year-old, 2 to 6-year-old, and then 6 to 18. Why is 6 to 18 in one group? Anyone have any idea? baby head size is pretty much same as adult up to the age of 6. So after age of 6, the head doesn't really get larger than it is. So the data was organized because it doesn't matter 6 or 18-year-old. The size will be the same. And so you can see here as the age of the baby gets small, the dose gets, okay, there you go. The dose is lower, which makes sense because we all know, or you'll know now when I say it, that children are more sensitive to radiation than adults. So you do need to reduce the dose as the age of the child goes down. So you can see here that our numbers are decreasing with age, which is fantastic. That's exactly what we wanted, and that's the practice in the United States. For comparison, again, you can see the adult head dose, 49 to 57, and for the babies, 6 to 8, which is almost 6 to 18, which is almost an adult, was very close to that 49. And then similarly for the other exams that I just showed you, right here, like sinus or neck and so on. Now, how do you use this information? This is all published data. You can get these papers in your university library over here. If I'm a hospital in Nigeria and I want to know how am I doing for my patients, how am I at CT doses, what you're going to do is take your data, again, what Mohammed is doing, hopefully he'll be publishing that soon. He's going to take this data and he is going to compare it with the American College of Radiology data. So this table shows you head, chest, abdomen, pelvis. The first 2 columns show you what the papers I just mentioned data, and the last 2 columns shows you what the dose is at your facility. And I just highlighted 2 or 4 exams here to show you that in this one case, over here, you can see the DRL and AD is 25 to 31, but my facility is slightly higher. Not too high, a little high. You can make adjustments, but look at this one. In the 6 to 18 years, 55 to 75, way higher. These are fake numbers. This is not our facility, just fake numbers. But the point I'm trying to make is if you are over here and your lowest dose is the highest dose that is in the literature, there's something wrong with your setup. You are overdosing your patient. So this is how you use the data. You compare it to what's published, again, good solid statistical data, and make changes to your protocol to optimize your dose. It's an obstacle course, I don't want to fall. And then similarly, you can look at the graphical presentations of the diagnostic reference levels. This is again from our institution, and you can see our doses in blue and the ACR doses. So for some reason, my hospital, the head dose is much higher compared to the paper I just published, right, in 2017. Why is that? So that's when you start investigating why is your dose high. Our head exams are typically set at a little higher dose because of the scanners we have and because the doctors really want to see good gray, white matter differentiation. And so our doses are high, and we said that's fine, it's a little high, it's still below the 75th percentile, so we are okay. As long as you can justify why you're a little high, it's okay to do so. So in some cases we are a little high, but in general we agree with the American College of Radiology data. So in summary, diagnostic reference levels are typically set at 75th percentile of the dose distribution, and 50th percentile is the achievable dose, and you want to look at both of them to optimize your image quality and dose at your hospital. And the overriding clinical objective, as I said earlier, is you want to get optimized dose. You do not want to be the lowest dose because your goal is get the best image quality for your radiologist, right? What are they happy with? Can they make the diagnosis at a certain dose level? Because as physicists, we want to say, no, go low in dose, but you have to understand the clinical component. What are they looking at? And you may have to modify, instead of calling it lowest dose, I like to say optimize your dose, whatever the doctor needs, but reasonable. You have to still educate them here is what everyone is doing, we are here too high, we do need to come down, what we are doing is not right. But you have to work with them, your radiologists, your technologists, to make sure your protocols are optimized. And I talked about the papers that we published in the US, and one starting point is looking at, the work Mohammed is doing with his doses. He can compare to that paper and see how the one hospital in Abuja is doing, and then hopefully get data from all hospitals and establish achievable dose and diagnostic reference levels here in Nigeria. And again, I think Joey mentioned this, but I also wanted to mention it that, we pay a lot of attention to dose and dose metrics, and we have to monitor dose, and the patient dose should be low. But we have to keep in mind the benefit that the patient is getting from CT, right? We're not just doing CT for fun. We're doing it to get a diagnosis, right? Joey mentioned earlier, in many, many years ago when there was no CT, and you're trying to figure out the source of pain, you may have to go into surgery to see what's going on, right? Now you do a CT and can tell there's something wrong with the appendix, or there's a tumor, or there's bleeding going on. It has so much value and so much benefit, and patients get scared, and you have to educate them that getting that CT is for their benefit, and the risk from CT is far lower than going into surgery and worrying about all the risks with surgery. Of course, at the same time, we want to make sure all our clinical exams are optimized, our doses are intended for the clinical reasons that we're doing the exam. So there is no evidence that I am aware of that says you get cancer because of CT. There is no evidence. You cannot establish that correlation at all because CT doses are so low, and just living in this environment, we are exposed to natural radiation. So even though there are papers like the controversial one Joey showed, you have to take that with a grain of salt. There is no evidence that radiation causes radiation causes cancer. You have to be very careful when you say statements like that. Such predictions are subject to a lot of uncertainty, should not be used to influence decision for justified procedures. So, there are patients who say, oh, I had 5 CTs in the last 2 months. I don't want to get another CT. Well, you have to, depending on your clinical issue that you have, and stop worrying that you're getting cancer from the CT, because it's really diagnosing your problem and giving you treatment to save your life. So you have to educate your patients, and you have to educate your staff as well that there is a benefit to doing the CT as long as your CT scanners are optimized. And as I said here, last statement, anticipated benefits to the patient from a necessary diagnostic imaging substantially outweigh any potential radiation risks. Thank you very much. So this is our campus, University of Washington in Seattle. This is our main campus. We have a lot of cherry blossom trees. We have a fountain, and that's our stadium where our team plays sports. And there's water and mountains. So Seattle is mainly surrounded by water. I wish we had put some more pictures of Seattle in our talks, but this is what it gives you. That's our hospital. The gray building is one of the hospital buildings, but so Joey and I work in the hospital. We don't work on the upper campus like here, this university. We are mainly based in the hospital. So I don't know if you want to take a 5-minute break or you want me to go into my next talk. Up to you. Anyone need a 5-minute stretch break? No? Keep going? All right. Let's do that. Just take a water break.
That's great.
All right. So we are going to completely change topics.
Yes.
Okay? I was asked to give this talk on artificial intelligence and medical physics. So I want to acknowledge my colleague Daniel, who Mohammed knows very well. He is more of an AI expert than I am. So I took a lot of some of his slides and modified them and added some of my own, but I want to give him credit. And then Department of Radiology, my radiology department, we have an AI committee. I'm on that committee. So everything I have learned is from being on that committee for the last 2-3 years. And the biggest disclaimer, I am not an AI expert, okay? So I will do my best with what knowledge I have learned as a medical physicist, but what I am presenting is based on my understanding after participating in my department's AI committee, talking to Daniel, and just general AI interest that I have, but by no extent I'm an expert. But because I was asked to give the talk by you, I will do my best, okay? All right, so let's get into AI. So first question, how many people here know what AI is? Everybody? Right? Can't escape it, right? It's everywhere. It's in our phones, it's in our cameras, it's, you go to the train station, AI is everywhere, right? So what is AI? It is a machine-based system that can, for a given set of human-defined objectives, make predictions, recommendations, or decisions influencing real or virtual environments. Basically, it's an automated system that does the job, as they say, of a human. I don't think it's completely human, but sort of try to get a machine to do a human's job. An example of AI is an imaging system that could use algorithms to give you diagnostic information for, say, skin cancer in patients. So if you had an algorithm running on one of your CT scanners that gave you the prediction of what are the chances this patient has skin cancer based on what you're looking at on images, that's an example of AI, okay? What is machine learning? How many of you have heard the word machine learning? Yes, maybe some of you. So machine learning is a set of techniques that can be used to train that AI algorithm to improve performance on a task-based data. So machine learning is a process by which computers, including AI, learn new things. So you're writing that machine learning software and you're feeding that into the AI algorithm to give you more accurate data. Does that make sense? Okay, excellent. So the problem is, AI, there are so many different types of algorithms. What this slide is showing is that if I'm trying to look at the noise on a CT image, I could use these 6 algorithms, and each of those algorithms gives me a different image, as you can see at the bottom. So I have algorithms, Lodo CT, NDCT, there's a red CNN, and a bunch of others. Different AI algorithms that I use to reduce the noise in an image, and you can see the image quality at the bottom. What do you know which one is correct? How do you know which one is correct, right? So yes, there is AI, but how do you know what AI you're using is appropriate or not? So when you're using something, you have to be careful that should I be introducing this in the clinic, and how accurate is this software? So the point of this slide was to show you, depending on what you use, you might get a different look on your image. However, there are benefits of AI in healthcare. So let's go through some of them, right? It helps in prediction of various risks and diseases. As I said, you could use an algorithm. It could scan your CT image and say, okay, there's a 50% chance this person has, a tumor or something. It helps in prevention and control of various diseases. It leads to better data-driven decisions because now you're using algorithms to automatically give you data. It can assist in improving surgery, support mental health, many different functions where you can use AI for the benefit of healthcare. In terms of economic and social benefits, it can help reduce costs. If you are treated early or diagnosed early, treatment costs is less. Cost savings with clinical trials, patient empowerment, you getting the power to look at your own treatment, to understand what is going on, and relieving workload. That's really what it's being used for primarily now, right? Like, so in radiology, you take a CT image, you run it through an AI algorithm, that algorithm tells you that this is a normal study or this is an abnormal study. So they've already done the job. Then the radiologist comes in, looks at the same study and says, oh yeah, I agree with the AI algorithm, it's a normal study. So it does reduce the medical practitioner's workload because it's already giving you the data or the result before you start even diagnosing the images. But what are the risks of AI in healthcare? We all know there are benefits. What are the risks? Well, AI diagnosis is not superior always to human beings, right? We are human. What does AI not have that we have? Anyone know? What AI has that we doesn't have that we have? Feelings? Did someone say feelings? Emotion? Right? The ability to think, right? Because AI is a machine. What you put in it is what it's giving out, and it's not always correct. So the AI diagnosis is not always superior to us as humans. We are much more superior just with our intelligence and emotions and feelings. So that's a risk. AI programs may be difficult to understand and overly ambitious. Totally agree with that, right? I don't do any programming, but what algorithms you are, how do you understand it? Are they difficult and are they over ambitious? Are they tested on a large number of data sets? I don't think so, right? There's implementation bias. So if I was a company that was selling an AI product and I trained my AI algorithm on 100 patients, 100 patients or whatever, and then I sold that to you. That is my 100 patients. When you incorporate it in your hospital, you have a lot of patients, population might be different. There is implementation issues, right? That may not work for you as it did for me. Transparency issues and risks with data sharing. How often do we tell people that the diagnosis we made was done with the help of AI? Nobody does that, but we are using AI every day. A lot of biases depending on population and then mistakes in disease diagnosis or AI cannot be held accountable. So if you mess up as a hospital on a patient's diagnosis, you're going to get sued, not the AI algorithm, right? So mistakes can be made by the algorithm, but you as a human are held accountable. So you have to make sure that if you are implementing it, you know what that AI algorithm is doing in your hospital. Data availability of the AI, what is it doing? We have asked our AI vendors for data. It's a black box. You don't really know what they're doing. Accessibility to the data that the AI algorithm is producing, that's also very difficult to get hold of. Are there any regulation concerns? You're using AI, social challenges, how many people will understand what it is and how to use it. So there are a lot of risks in using AI in healthcare. So here are a couple of articles that were published. Researchers say an AI-powered transcription tool used in hospitals invents things no one has ever said. Okay? Is there a problem with that? Right? It's saying things that no one has ever said. It's an AI-powered transcription tool. Everyone know what a transcription tool is? It transcribes what the radiologist is saying for the report. So if I'm a radiologist reading a CT report, I'm transcribing, I see this is this. So in this hospital, there was an AI transcription tool and it produced a report which no one understood. It said things that no one ever said. So there was an error in that AI algorithm. The other one says AI coding tool wipes out production database, fabricates 4,000 users, all fake data, right? Google's healthcare AI made up a body part. It made up a body part, seriously. What happens when doctors don't notice? So the point I'm trying to make with this slide is you want to use AI because it's useful, but you need to keep an eye on it as a tool. Like, what is it doing? Is it causing errors? Is it making mistakes? Because if it makes mistakes and you don't do anything, you're in trouble. Which leads to the topic that I think physicists need to be involved in is governance in AI. So there are all these, and no one is doing anything about monitoring them. So we just spoke a few minutes ago about monitoring dose, right? Everyone agree we should monitor dose? right? So should we be monitoring AI? Right? Makes sense. So governance in AI, that's what this is about. It is a process for managing imaging AI tools, software and algorithms applied to medical imaging and the practice of medicine. So I feel when I got involved in AI, I went and talked to the radiologist and said, this is cool, you're using AI. Who's monitoring it? And he looked very blankly at me and said, question, right? As physicists, that's what we do. We do quality assurance, we do quality control. So governance is extremely important. And now, at least in the United States, people are giving more importance to governance. And we need to be able to monitor these AI algorithms to ensure they are working the way they should. So governance of AI models in medicine, it's AI in imaging has exploded. I mean, it is ridiculous. I think as I speak, 2 algorithms are getting approved, right? There are more than 700 FDA cleared models. So for those of you who don't know, FDA is the federal government department that approves in the United States. Unless they don't approve it, you can't use it. So more than 700 FDA approved algorithms and models. Most of those are radiology. Most of those are radiology. I don't have the exact number with me, but most of them are. So you're using model proliferation, you're more and more are being FDA approved, you're using it in your clinic side, right? There's inconsistent off-label use of AI tools, no 2 hospitals use AI tools exactly the same. It takes years to fix an error. So like the previous slide where I showed you some of those risks that AI, said it invented an organ not found in the human anatomy, or it had transcription errors, saying things that no one said. It's years to find and fix those errors. So you need to be on top of things to make sure your AI is behaving the way it should. So in the US, the American College of Radiology again has a recognized Center for Healthcare. They call it the ARPNRG AI program. And it basically, I don't know if you can read that, I can't. It basically, the criteria for a site to be considered an ARC site is if you have established an AI governance tool. So basically, just like you're doing quality control or dose registry for radiation dose, we're trying to now establish or give hospitals the opportunity to get involved in this, be a recognized health center where you can proudly say that, yes, I'm governing my AI algorithms. And that first line that I have highlighted there is establishing a multidisciplinary governance group, which is what we did. So you can see that University of Washington, UW Medicine, which is our hospital, is one of the AI recognized sites because we do govern all our AI algorithms along with other hospitals in the US. So why do you want to have governance? I hope I've convinced you by now, but if I haven't, these are some of the reasons. AI models do not always generalize well to new data. If you suddenly got new data, and I'll show you an example later, is your AI algorithm adjusting to that, right? It may not be doing that. How does it do with your patient's population? So if I had AI at a hospital that does adult patients, and then I move that same tool to a hospital that had pediatric patients, is my AI going to perform the same way? How does it do with drift? How does it do with time? Again, I don't know the practice of medical physics so well in Nigeria, but in the US, Joey and I are testing all our machines once a year to make sure our radiation levels are same, there's no drift, nothing is broken. Similar concept you want to apply to AI, right? How well does it perform or drift after some time? If I bought the AI today, in a month, 6 months, a year, is it going to perform the same? So that's what you have to worry about. Is there an update on the model? Did they do a software? All of us have computers. You get software updates, things break down. You see that on your computer. What if the AI model gets an update? Have you checked whether it's still behaving the way it should? Did you buy new imaging equipment? Did you buy a new CT scanner? Did you upgrade your software? Has your patient demographics changed? As I said, did you go from adult to a pediatric patient? Is it behaving the way it should? Or new or change in disease? Is it going to be able to diagnose new diseases or any changes from how disease processes works or physiology works? And there are many, many competing methods to do this. You need a method to decide how do you govern AI models. You also have to educate users and team on how to use AI models safely, efficiently, and effectively. As I said before, I asked that question to my radiologist. I don't think anyone in our department was looking at our AI models, right? We then formed this AI committee, and the goal here is to use AI tools safely, effectively, and efficiently. And so you need a quality assurance, quality control process to measure all of these things that I just mentioned, just like we do for radiation as medical physicists. So we just have to take out our imaging equipment testing hat and put on our AI quality assurance, quality control hat and try and figure out a method. How do we do this to ensure our AI models are behaving the way they should? So then the question comes, why physicists? I was asked to talk about AI and medical physicists. So why us, right? Whoever in the room is a physicist. Why physicists? Well, we already take care of quality control. We are the stewards of quality control. This table or this graph, this slide shows you all the organizations in the United States that deal with quality control that we as physicists adhere to. So the American College of Radiology, they accredit our CT scanners, so we have to follow their quality control. We have state regulations. In my state where we live in the state of Washington, they have their own regulation. We adhere to that. There's Joint Commission that comes to accredit hospitals. They have their own quality control requirements. As physicists, we adhere to that, right? And then they're members of AAPM. Whatever AAPM comes out with, we adhere to that. So we are already doing this. We are the experts in quality control. That's why physicists are very well positioned to do governance in AI. So here is a wonderful diagram that actually Jody prepared for us for when he was a resident, and we were starting out and figuring out how to do governance for AI, and it's too much to read. I'll try and summarize what we are trying to do. So say I have a doctor who comes and tells me, I have this cool AI algorithm, I want to implement it in our clinic in radiology at University of Washington. This governance document is what we wrote when someone comes to us with a request. So from the request all the way to approval, if approved. So the steps on the left that I put in that bubble over there kind of highlight a little bit of what we would do. So you would have a pre-intake scoping, right? So if you came to me, pre-intake scoping, do your research, figure out what that's about. They would fill in an intake form, right? They would say, I'm the doctor, here is the product, this is the data they use it on, here is the specificity, here's the sensitivity, so on. We take that information from the doctor, that's the intake process. You review it to make sure, does that make sense? Do we have something already in place in the department that pays the same? Then you look at your money, right, budgeting. They are not cheap. Like anything else you buy, it's not cheap. So then you have to figure out, okay, this looks like it's worthy, but where is it in my budget list? Do I want to spend $1 million on CT scanner, or do I want to spend whatever on an AI algorithm? So then the budgeting comes into effect, and then implementation. Okay, then the next step is how do we implement it, and education and performance monitoring. So you have to make sure once you implemented it, how are you going to monitor it while you're using it? Similar steps to what we do maybe even in dose monitoring. When you're buying a new piece of equipment, you want to understand what the technology is, what technical details the CT scanner has, how expensive it is, and so on and so forth. Similar process. But we wanted to come up with a little bit of a formal process so that if I have 5 doctors telling me they want to implement AI algorithm, they all go through this process. And if 3 of them are basically pitching or requesting 3 different ones which are doing the same thing, you could then tell them, okay guys, out of these 3, you're going to pick one because it does the same thing. So you have to have a process so that you do not carelessly just implement AI without doing something about it. So here's our role, I think, and Daniel thinks, we talked about this, physicists' role in AI governance. So we should have general oversight. At least we should be sitting at the table when the radiologists are talking, at least give our valuable input from our experience with what we do with imaging equipment. So general oversight, purchasing, we should be involved in how are we going to implement it, how are we going to train the radiologists, and how are we going to do longitudinal surveillance. And I think that is the biggest problem. As physicists, because we do that already, we really can provide our experience and expertise to help the radiologists understand surveillance, longitudinal surveillance. So let's talk about each of these. So general oversight is basically make sure you're involved, right? You're a committee member. As I said, about 5 years ago, I decided as medical physicists, nobody in my team is doing AI. How do I make sure that my team is not left behind as my department goes forward with AI? So I approached one of my radiologists who was doing a lot of informatics and AI, and I said, I want to be involved. Or I asked a difficult question, how are you doing QA? And he said, okay, you're on the committee, which was the best thing that happened to me because I learned a lot about it, right? So you want to be on a committee, you want to have a voice at the table, you want to help with designing the policy, review any intakes that come in, figure out how to use your local data set, and then how would you test and analyze, right? So first thing, be invited to the discussion. And then what model are you going to govern? There are so many types. I showed you that first slide for reducing noise and how many different algorithms are there. So be specific. Are you doing AI and machine learning models that you're trying to govern? Are you doing pixel-based data? Are you doing something that is beyond your scope? Things like that. So is it an LLM, large language machine language? Is it CAD AI? Is it segmentation? Or is it image reconstruction? So there are so many different things. Which one are you going to govern, right? For us, we started out first with purely diagnosis type of AI. Because the machines, the CT scanners, as I'll show you in a minute, they already come with FDA-approved AI processes. So the question we asked, we need to monitor those. And initially we said we won't do it, but we feel now that we need to monitor those as well. Because it's, again, we need to test it on our population. What is the role of the model that you're adopting in assessing risk? Is it a low-risk model, like just patient-centering, which doesn't really, have too much impact, has an impact on dose, but it's still low risk? Is it medium risk of metal detection, or is it high risk of unsupervised diagnosis? As well as image reconstruction, the AI algorithms that could introduce things in the image that were not there before you did the AI on it. So that is very much possible, and that is high risk, right? If they're introducing things that are not in an image, and if you're not supervising the diagnosis that AI is giving. So that's considered high risk. So depending on the model and the question, is it high risk, low risk, medium risk? You try to assess that. This is a very busy table. I don't expect you to read it. What I'm showing here is we put together a Excel spreadsheet of all of our CT scanners and our MR scanners that have AI in them. So, we have AI, what the tool was, which is the column over here. This is the AI tool, machine learning or AI. And then what was the purpose of that AI tool? So these CT scanners already come with that. How many of us have done anything with them? How many of us have governed it? So even forget diagnosis AI, just think of what's in your CT scanner and MR scanner, and what are you doing about it, right? So when we got like True Fidelity or DSLR, it's tired. Yeah. Well, I'm sure like all of you. Okay, it's like if you get there you go. Yeah. I'll try and steer it from that. Yeah. If you get like DLIR, which is an AI processing for image reconstruction of your CT scanner, how many of you have tested that, right? So things like that, I'm just giving you an example that your own CT scanners and MR scanners already have AI. and we don't do much with it. We need to when you are trying to adopt them for diagnosis. What happens when a test fails, right? The model's already purchased, the CT scanner's already purchased, they're all bundled into the scanners. You need to be able to identify constraints of model performance. When does it fail? What do you do when it fails? And it will fail if you do this and if you don't do this, things like that. So what happens when a test fails is important. So that's all those initial part. Purchasing. Do you want to buy this product? Is it worth it? Just like the amount of time and energy and research you do when you want to buy a new CT scanner, you need to do the same evaluation when you're buying an AI algorithm or an AI product. Do we have another product that performs the same way? As I said, if 3 doctors come to me with the same idea, but propose 3 different AI, I'll give you an example right now. We are right now looking at doing opportunistic CT screening for osteoporosis. And I have 3 different doctors who are saying, oh, let's buy this software. One is saying, let's buy this software. One is saying, let's buy this software. They come to the AI committee, and we will decide as a committee, saying, okay, guys, let's evaluate this. And we think all 3 of you will be satisfied if we use this software. So I think that's very important that you don't buy 5 different softwares that's going to do the same thing, right? So do we have another product that performs this task already? Understand model architecture. How does this work, right? How, just like with your dose monitoring systems, you have to understand how they integrate with your scanners, with your IT, with your network. You have to understand model architecture for AI as well. Consider DICOM tags, what recon types, matrix size, bit depth, all things that you look at when you are looking at these products. And then how do you implement it? So say we said, all right, you're going to buy this, now let's implement it. You don't just implement it. You have to explain this to your radiologists, your technologists, and I would say physicists as well. I think physicists need to be involved. Where does physics come in? I forgot to make that font from black to white, but you can still read it. Well, we are involved, I think, in all aspects of this process. We should be there at the table. We should be there when they're implementing. We should be there when they are surveilling. I think physics needs to be involved in all of them. And you'll say, okay, well, I don't know anything about AI. Hey, if I can do it, you can do it. I didn't know anything about AI, right? I got on the committee. I have been listening for 5 years, and I was practicing this talk with my colleague who's much more of an AI expert. He told me, you don't even know this stuff. And so I have obviously absorbed it, but I didn't think I had, right? I didn't by any stretch of the imagination feel I'm an expert. But you pick it up, you learn, and I think you have to take that first step as a physicist and be involved in making sure you are invited to the conversation. So this just shows you the expectation, right? The local data, your demographics, your equipment, your protocols are all different than what the training data that was used by the company that sold you the AI product. And in reality, this is how it is, right? In reality, they use 200, 300, 500 cases to train their AI. The big circle on the left is our data. We do thousands and thousands of patients in a year. So our data and data set is huge. And the reality is that you need to make sure that whatever training data they use and whatever population, your patient population is, you're going to still get out of the algorithm what they are saying is accuracy or the specificity or the sensitivity. Again, local baseline might look like this. Local post baseline might look like that. Your goal is that they should pretty much be the same. Basically, what I'm trying to say is, if your algorithm said it will do this, when you implement, that's what it should do. It should not change based on your demographics and your population. And there are different types of patient data, right? There are types of data. There's patient data, end-to-end testing. You want to make sure it works for everything, or you have phantom-based data. Joey showed the CT phantom. You could do some testing with just phantoms to see how it behaves, but that's not what they're using. They're using actual patient data. And you have to look at the drift. You have to see why it's different and what's going on. So here's an example. Again, I don't expect you to read it, But here's an example. Once we have approved, the AI committee has approved an algorithm, we have these model cards that we post in the reading room. So this is ADOC is our AI vendor, and it was a AI tool to detect acute pulmonary embolism on chest CT. So it was a PE protocol. And it's telling you, it's showing you the clinical workflow. It's saying, what did the FDA approve, right? On the left, it's saying, okay, it said it would be 94.4% accurate. What is their N 499 cases is what they trained in. My data on the right at my hospital, let me rush, hurry up. It's saying it's 99% accurate and it was done on more than 5,000 or patients. So we are confident with our data, so we collect data when we implement it, we do these analysis, sensitivity, specificity, the positive predictive value, and so on, and we post this in our so that the doctors know, okay, yeah, this is working all right, this is the algorithm, it's working great, it's perfect. The point here is you do not want to take what the vendor says and take their word for it. You need to do your own analysis and make sure it's behaving the way it should behave with your patient population. So we do this for all our AI algorithms, and as I said, they're posted. The issue is now you got this, it's implemented, how do you keep monitoring it? And how do you train and educate? So you have the AI model, we have classified everything as I showed in the model card, but you need to think about imaging parameters for CT, artifacts, did you upgrade or update your CT scanner? Has anything changed since you implemented the AI protocol, right, or the algorithm? So you need to do longitudinal assessment. So once you're implemented, you're not done. You need to assess it, keep continuing, otherwise it defeats the purpose. You just bought this Ferrari and then you're not giving it oil to run, right? You have to make sure it's well maintained and it's going to run for a long period of time. Again, your local post baseline data and then what the local base data was at baseline and then later over time should match. Again, to show you again where the physics come in, pretty much I say in every step of the process as much as possible. I'm going to skip this slide and talk a little bit about data drift. So we implemented that. Now, how to make sure it's going to behave the way it does, right? So data drift is defined as a systematic shift in the underlying distribution of input features that can cause model performance to deteriorate or behave in unexpected ways, which can pose a threat to the safety of patients. All that is saying is, did something change that would impact the output of the algorithm? And that's what you have to try to monitor, the drift. Detecting this drift is really difficult. You have to be proactive and you have to intervene before it causes harm to the patient. So what if my algorithm suddenly changed and started seeing tumors in normal images? That's a problem. Because in that patient, you're going to tell them they have a tumor and they don't. So there's the emotional and psychological risk, as well as the treatment and cost and so on, right? So you don't want that. So you need to be able to intervene or catch the problem before it harms your patient. It's therefore vital that deployed algorithms are monitored for drift in the populations they serve, not the population that the algorithm was approved of, for the population that you have in your hospital. So I'm going to show you one, I just have 2 slides left. I'm going to show you an example of what happens if you don't monitor your algorithm. This is a very busy slide. Let's see if we can get through it together. So this is showing you data from a hospital. The x-axis is timestamp, 2019. What happened in 2020? Everyone remember in the world? COVID, right? So this is showing you a hospital showing data from its AI algorithm. The blue line at the top is just area under the curve, which we have all used as statistics. And it's showing you it's straightforward. It's nothing is changing between 2019 all the way to 2020. That area under the curve is staying constant. Basically, if you were using that monitoring method, it's saying everything is fine with your AI algorithm. But if you use, and again, I'm not an expert on this, but if you use auto encoders, which basically are much more sophisticated ways of looking at trends or drifts, you can see what happens. So all of this green is what the auto encoder detected. Here is your p-value at the 0.05 level, right? Anything below that is significant. But what it's showing is how that green area, your algorithm totally changed behavior once this hospital started getting COVID patients. And this was for, I believe it was for a chest algorithm, but I don't recall right now. But the point I'm trying to make is your data just totally messed up now, because now you're seeing patients not with clear chest, you're having COVID type symptoms, right? Those glass pebble type appearance in the lungs. And your algorithm did not behave the way it should have. So the point again here is you have to use analysis tools that can pick up that change in behavior. Again, I don't know much about the autoencoder, but we are going to try it right now on our MR and CT technologist QC data, because we have a lot of that. So we're going to try this to see and test it with an AI algorithm to see if it detects any change, which will be very cool. But again, the point here is you need to have some kind of surveillance. What you use, you have to educate yourself. As I said, I don't know much about autoencoders, but that is what is a much better, more sensitive tool than just doing an area under the curve, and you can see that that does not show any behavior. So over time here, the algorithm did not behave well at all when you started seeing COVID patients. So similarly, if your population changes for a reason, you need to reassess if that AI algorithm is applicable to that population. So in summary, I'm almost done. There is a physics role in AI, especially in AI governance. You know, you can be involved at the table purchasing, whether that's a good product or not, implementation, training, quality control, and I think more importantly, just doing longitudinal surveillance. And why? We are used to that. We do that for everything else in medical physics, right? So we know about quality control. We know about doing it annually. We know about testing our systems when there's major repair. So I think we are very, very appropriate people and profession to be involved in AI governance. And that's it. Thank you so much. Come up here, Joey. If you have any questions for Joey or me, we can answer them now.
Thank you very much for that presentation. So we'll be taking questions now. Before we take 5 from our physical audience here, and then we'll pick some of our virtual participants. So can we take 5 people? Questions? 1. I have more of that question. Then you, as you ask your question, please introduce yourself and also direct your question.
For whom the question is.
Let's just take some and then we'll see how far we could go.
Thank you very much, the presenters. My name is Abdullahi Hassan, and I'm a PhD student from Federal University, Latvia, in Zaria State University. Also, at the same time, I'm a staff of the Nigerian Nuclear Regulatory Authority, which is the body responsible for regulating medical practices in diagnostic radiology, medicine, radiotherapy as well. So basically, my first questions are, we actually need to measure effective dose, because even the ICRP does not actually recommend effective dose as one of the RL quantity. So do we actually need to measure, maybe, let's say if you want to establish a national diagnostic reference levels. And what can you say a bit about the FDA, I mean, Food Drugs Administrator, your American FDA CTDI? What's the difference between it and the volume CTDI? Also, I'm just wondering, why is SS more frequently measured for pediatric, not necessarily on adults? Because I've seen a lot of articles, mostly you just see such measurements on pediatric measurements, and also about the 50th percentile, the achievable dose. Is that also necessary? I can understand that the ACR may have recommended in America, but also the ICRP does not actually much recommend in establishing ARL to measure the achievable dose. They mostly recommend 75th percentile. So is it necessary that we should add it, or is it just for an academic exercise, basically?
Yeah,
Well, let's answer the question before we go to someone else.
I'll see if I can tackle those one at a time, and I'll pass on as needed. To start with the effective dose measurement, I think effective dose is a fraught measurement for what it's become used for. I think it was developed as a way to compare doses between modalities. Right? If you have a CTDI ball from a CT study and you want to compare to dose area product from an interventional fluoroscopy procedure, you can't compare DAP to CTDI, but you can compare effective dose between fluoroscopy and CT. So if you're just comparing modalities, I think effective dose is a good metric to use because it accounts for the radiation type and the region of radiation interaction, accounting for different radiosensitivities of different organs. Now we're getting more sophisticated. There are new models coming out based on organ doses specifically and measure lifetime attributable risk. I would direct you to some of the recent research out of specifically Dr. Isan Sameh. He is doing innovative research here looking at the best metric for sort of cancer risk in particular. But those are sort of my thoughts there. People use it too far to assign patient-specific cancer risk for which it should not be used. So I hope that addresses your question. There was a question about CTDI versus the FDA CTDI ball. To my knowledge, the FDA just requires that the CTDI and the DLP are available for every study captured in the dose report. To my knowledge, there's just one definition of CTDI ball, and it is explicitly defined by reports from the AAPM and now adopted by vendors when testing their systems. And to my knowledge, adopted by the FDA as well. What was the third question?
SSDE.
Oh yeah, SSDE. I am not as aware as you seem to be on SSDE being used more specifically for pediatrics. I suppose my one sort of assumption there would just be that patients have a much wider range in size as they develop. Calvin mentioned ages 6 to 18 being sort of fixed for head examinations, and of course, head is going to be pretty much similar across the board for all adults. So SSDE for specifically head exams might be more appropriate for pediatric populations where you actually have changes in that 0 to 6 range. And if anything, just out of an abundance of caution for the increased radiosensitivity of younger populations and SSDE being more accurate. And then I'll let you handle the achievable dose DRL question.
What was the question? I forgot.
In many literatures.
Oh, the 50th percentile or something, yeah. So the 75th percentile is a threshold, right, at which, beyond which you start investigating if your dose is high. But if you want to see where you are at average doses, 50th percentile is also what ACR recommends. And that's, if you're doing 75th percentile, calculating 50th percentile is not difficult, right? You're already doing one. Your goal should be to be as close to 50th percentile, or definitely between the 50th and the 75th percentile. So I think I would highly recommend that you also calculate the 80 or achievable dose.
Thank you. My name is Dr. Ahmadu. I'm the head of department, medical radiography. I have a question to Prof. Ma. How effective will CT dose measurement be in a machine that's more than 10 years? Number two, how do CT dose reference level affect racial differences? And number three, how does ongoing research on local CT dose reference level compare the established local dose? Thank you, ma'am.
I missed the first question. Let me take.
The first question I'm asking of the effectiveness of measuring CT dose in older machine of more than 70 years and above. I came to understand that most of our machine here in Nigeria is not the newer machines. We operate them for more than 10 years, even above. So how effective is measurement of CT dose reference will be correct?
Okay, so you're basically saying you have older generation of CT scanners and whether it would be effective to do DRL measurements on that.
Yes, ma'am.
I think absolutely. CT machine is a CT machine, old or new. The newer machines actually have more dose saving options compared to the older machines. So I think it's even more important to measure and monitor the dose on the old machines. Now, the DRLs that are established there is no, for the American College of Radiology data, it does not give you the dose as a function of which CT model it is. It just gives you general information. So I think it's still a good number for you to compare it to, but it's possible in your old scanners, like you may not have automatic tube current modulation. So you're using manual MA, for example, it's still worthwhile to monitor your dose for your older scanners. I mean, we had a 16-slice scanner. When I first came to University of Washington, we had a single-slice scanner. That was 25 years ago. And we just got rid of our 16-slice scanners like the last one last year. So we were still monitoring dose on those scanners, even though we have a 256-slice CT scanner. So I think, yes, you should continue to do measurements and compare to DRL values. The second question was about, how does racial population? Yes, absolutely. That's why it is important to establish DRLs in your own country, right? So the DRL papers we publish are for the US population. If I take that same methodology and apply it to, say, Japan, where people are tinier or smaller, the DRL values might be different. I mentioned in my presentation that we compare our data to 8 countries. So there are many countries that do establish their own DRLs, and I highly recommend that, and that's what we have been talking to Mohammed about. So yes, there will be differences in population, and of course what type of CT scanners you have, that will impact your DRL values. And DRL values should, once they're established, that's not the end of the world. You have to keep monitoring and keep establishing it. So my paper is already outdated, right? The ACR needs to now establish DRLs and see what has changed, because a lot can change. You might buy new machines, you might have more dose-saving options, your DRLs will change. So absolutely it has an impact and you should do that. And similarly, for your third question, you should establish local DRLs. But having comparison benchmarks is a good way, right? Even if you did local DRL, how do you know you're in the ballpark? So let's see what US has, and let's see what Japan has, let's see what Australia has. Because every country has published DRLs, and you can compare to them. And then, depending on your population, see if you're higher, why you're higher, and try to optimize your protocols to come down in those. Hope that answers your question.
I'm Professor Lal Suleiman, Institute of Radiology. I want to commend Professor for the presentation. Well articulated. Folks who are doing questions are actually, sorry, I want to talk about the image you projected. Skin erythema. Halos.
Yes.
I want to say it's not, as you said, it's very rare. But I want to say in the diagnostic range of radiation dose, you don't have what they have, physical have. What you have is physical effect. Those cases, as you said, maybe from repetition of the same examination. But it's really not established. Even the stochastic,
Yes, so let me just address what you said. So this exam is very common in the United States. It's called the CT head perfusion exam. So what they do is they scan the same area of the skin in the head over and over because you're looking for bleeds. So you do CT head perfusion exams, you're looking at bleeds and blood flow, and so same area of the skin is exposed. So I understand what you're saying, you don't see it in CT, but for some exams there is a risk because you are head perfusion exam, which is why these patients have the effect, is because you're scanning the same area and so you cross that threshold of too gray to potentially cause skin. But your point is well taken. Typically in CT, we will not see such high doses to cause the effect.
My second question is that have you done a follow-up study on patients examinations, like a longitudinal study?
So you're talking about cumulative dose. Yeah, so our dose monitoring software does give us cumulative dose, but we have not really done anything with it, and the reason I feel that it's not worth it for us to do that for stochastic effects. First of all, the body generates cells every 24 hours. So if I go to CT today and I get a CT next week, to me it's a different cells that are being exposed to the radiation. We have not paid a lot of attention to that because we think it's important, but not that important in summing up that cumulative risk, because again, it's not the same cells that are being exposed. But there is a lot of research out there. Dr. Madan Rehani actually has published a lot on cumulative dose, if that's what you're asking.
I think maybe you need to talk more about how do we come about drug dose? How do we measure drug dose?
How do we measure drug dose? Yeah, so that's a very difficult question unless you have, you can't go inside a patient's body and measure drug dose, right? So there are a lot of computer modeling that you can do, either based on phantom data or actually on organ, virtual organs that you have. Like again, Duke has done a lot of work on this. There are software that's available that gives you a more realistic absorbed dose information. You could use dosimeters and put it on the skin, at least get surface dose accuracy, and then try and use attenuation and depth information to kind of come up with that surface. So I would say I would go, if I had to do it, we only use computer algorithm software to calculate absorbed dose, because it's not accurate science, right? It's an estimate based on Monte Carlo calculation. So as long as you have a ballpark, it's good enough. And we do that all the time to calculate fetal dose, and which helps us determine is there a risk from that exam for that fetus.
My last question is a local researcher here, Ahmad. I was wondering initially, you had your study done while here, I have a CT scanner. I don't know what.
Okay, thank you, Prof. Because I reside in Abuja, yes, apart from Abuja, we're planning on research to other institutions.
Good afternoon. Thank you very much for your lecture. I appreciate that. The knowledge you shared has been impactful. My question goes to Prof. Opana. Basically, I just want to get what your feel is, what your mindset would be if, because no, it's basically towards your AI presentation. What is your mindset? What do you feel? How comfortable would you be with artificial intelligence integration if maybe their algorithm impute machine learning into the actual functioning of the AIs? What do I mean? Let's assume a situation where as images are being acquired, as analysis are being done on the reports of those diagnoses, you have a situation where probably the facts, the icons are linked to the AI, and there's this continuous machine learning. Do you feel it will be, would you be rather comfortable with a connection between the functioning AI and machine learning to probably adjust the data drifts that might probably occur? Do you feel if these are done to aid better integration AI to both diagnosis, image reconstruction, and all of that generally, how do you feel important to help integrate AI? Because definitely we are not going back. AI is here to stay. So thank you. That's just basically. Thank you very much.
Sure. So if I understand your question, let me just repeat just to make sure. You're saying if I algorithm implemented, and at the same time I was doing continuous feeding of machine learning to keep improving the accuracy of the AI algorithm as I'm doing my diagnosis, correct? Yeah, I think that's a very good question, and I think that's not necessarily happening now, right? Because I think you have to upgrade the software and then use it. I think it would be great, but I think you would have to have some very solid monitoring tools that if you're continuously monitoring, how is that outcome changing? So I think it would be difficult to do. I showed you the model card that we put based on how it's behaving on one day. Okay, this is our behavior over the last 3 months. We published the data. For continuous optimizing of that AI, that's a little bit challenging. How are you going to continue doing that? And how do you know if that may have caused a problem? So I think it's a great idea, but we'd have to develop some great analytical tools and analysis tools to make sure you could do it continuously without impacting the effect on patients. Does that make sense?
Thank you. My name is Mohammed Nasser. I'm a student of life sciences from Department of Biochemistry. Yes, I think they like it because when they are listening, but you see, my curiosity about this lecture is actually arose from the fact that unit of life, and a group of cells working together, with the same function, you do tissue, and then you go to organ, and then you have the system. When Joe was making his presentation, actually what came up to mind, the question is actually for both of you.
Okay.
It's a cocktail of my understanding of your talk, actually. Okay. So I think any one of you can answer the question. And most of the questions actually were raised on the issue of CTDI and the SSD. But my question is a little bit practical. Joe was giving us a lectures on two types of scans, axial and helical. And then during the course of his presentation, he went to introduce another multiple axial scan. So in the process of optimization of the protocol for the DRL or the ADs, and then maybe comparing the global benchmarks, is it possible that we can actually use any of these three kind of scans that he has mentioned, either the helical or the axial or the multiple axial scan? Thank you very much.
Yes, I probably should have been a little bit more specific. The multiple scan average dose, where I had an upside down frowny face, is kind of an outdated metric that's been replaced by CTDI. And the axial versus helical discussion, we measure CTDI vol only in an axial configuration just for the sake of measurement, to keep our dosimeter still, basically. So that's just a practical measurement specification. We, in the clinic, correct for the dose of a helical scan by dividing by the pitch. And so the CTDI vol takes all of that into account and corrects between axial and helical. So the CTDI vol itself is pitch agnostic, and serves to be the sort of unifying comparator metric, if that makes sense.
And I want to add to that a little bit that CTDI concept is a little outdated. We need to really revisit dose metrics in CT because, as Jody mentioned earlier, it's to a phantom, the dose, it's not to a patient, right? And there have been studies where people are now exploring doing the measurement in air instead of in a phantom and trying to come up with a better indicator of a CT dose country. But in the DRLs, where the DRLs are concerned, it doesn't matter if one hospital does helical, one does axial. When you're measuring CTDI, you always have to do it in axial mode. And so the measurements that how you measure it, whether I measure it in Seattle, how you do it here in Zaria, same thing. We are measuring it exactly the same way. So the data that's getting inputting for CTDI is the same. As Joey said, in the calculation, the pitch and all that is taken care of. But when you're actually measuring the numbers, you're doing it in axial mode. Yeah. And again, CTDI, I think now we need to change it and we need to come up with better. I think the scientific community is looking into that in AAPM.
And that would also take cognizance the age of the machine that I think the person has raised the question.
Yeah, and when we did the DRL papers, a lot of people asked me, why can't you do the analysis as a function of CT model or age, or whether it's multi-slice or single slice? And we said, well, if the data is not in the DICOM header, if it's not defined in the DICOM header, we couldn't do that analysis because a lot of the data that every hospital was sending was all via DICOM header extraction. So things like that, I think there's a lot we can still do with dose monitoring. And I think AAPM is working on a lot of things to improve accuracy and the science behind dose monitoring.
Good afternoon, everyone. I'm Ismail Bello from Physics Department. My question here is about the tomography CT scan and dose length. When brain CT and abdominal CT. So can one compare the data taken for different patients? Maybe one that undergoes brain CT and one that undergoes abdominal CT scan as the dose length product and the computed tomography dose index.
Yeah, so the question regarding head versus body, you can compare with a big asterisk. I mentioned that there are two phantoms that you can measure CTDI vol for. There's a 16 centimeter phantom for the head and a 32 for the body. And you also need to make sure that when you're interpreting the dose coming off the machine, that it's standardized to the phantom you're expecting, right? So if you have a pediatric abdomen, some pediatric abdomens are closer to 16 centimeters, and so vendors will report the value for the 16 centimeter phantom. So you can't then very well add the CTDI ball for a head scan plus a body scan. You could use a correction, the discrepancy is only about a factor. And so if you had a CTDI measured in the head phantom of 40 milligray, you could estimate that the CTDI measured in the body phantom with the same scan would be around 20 or a little bit less. But the way that you would then get around that sort of speaks to our effective dose discussion, where once you have the DLP, depending on the phantom and the location of the scan, if you correct it to effective dose, you could add the effective dose of a head scan plus the effective dose of an abdomen scan. But certainly your comment gets complicated if a patient has a combination exam that runs, head to toe. You'd probably, if it were me, I would add the dose in the head section using the 16 centimeter, convert that to effective dose using the K factor, do the same thing for the body, and then I can add them together. But as long as you're being specific about which region and which phantom you're talking about, I think that you're apples to apples there. Does that answer your question?
Thank you. My question goes to Professor Kaplan. You said that there's no evidence that CT scanning. My question is, there a safe radiation dose?
I'm sorry, say it again?
I said, my question, because you said there was no evidence that CT scan has caused cancer. I said, is there a safe radiation dose?
Safe radiation. Safe. Oh, is there a safe radiation? Yes. So, interesting question. So, let me talk a little bit about how we know anything about the impact of radiation on dose, right? So, what all data we have as human beings is from the atomic bomb survivors, right? People who were exposed during the Hiroshima and Nagasaki atomic bomb attack, the survivors, they studied the impact, and that is still being studied. And we know, okay, here was the dose at that time, here was the effect, right? Whether it was stochastic or cancer or deterministic effect. Now we've taken that data, and come down and work in an area where CT is and establish risk. Right now, from what science tells us, from what AAPM position statements are, that anything below about 100 millisieverts there's not enough evidence to say it causes cancer. Okay? Now, depending on what paper you look at, you might get a lot of contradictory information. So I would say, look at authoritative radiology organizations and papers. So AAPM, American College of Radiology, the FDA. Right now, the risk at the levels we work with, diagnostic radiology, there is no risk. They're very low, the dose. But there are, as somebody asked the question, cumulative dose, right? There are some patients who might get a lot of scans. So then do we want to keep track of dose because of that? The case I showed you with the hair loss, if you're not monitoring and somehow you gave the patient a large dose, then you see that hair loss, which is not common. So I think a safe number, when I do any patient consulting for fetal dose especially, anything that is out there that's recommendation is what we follow. So right now AAPM says, anything below 100 millisieverts there's no substantial evidence to say it causes harm. But that doesn't mean that you need to increase your dose, right? You still want to compare your DRLs and still monitor the dose because we are human beings. We don't want to give more dose than needed. So, does that answer your question?
Just to add two things, Kalpana mentioned the atomic bomb survivors. The most conservative model and the one that is generally followed right now is the linear node threshold, which like we have that 100 millisievert line. We don't really know what happens in the lower region, but we're going to draw a dotted line and to assume that it's linear. But some people want to say that it actually is like hormetic, so some amount of radiation is actually good for us. So that question is still unanswered. And the paper that I cited that I mentioned having issue with, when you look at patients that get CT scans and then go on to develop cancer, the issue is they are getting a CT scan for a particular reason. And if they are getting a CT exam, they're probably more likely to have underlying conditions that would be related to cancer. And so is it the CT scan that caused it, or are they getting a CT scan because they're of suspicion?
Plus, again, to add to what you said, how are you going to distinguish that the cancer you got was from the CT? There are so many causes of cancer, the way we live, our lifestyle, what we eat, what we are exposed to, the environment. As we are sitting here, we are exposed to background radiation. How can you say for a fact that that CT that you got gave you cancer? There's absolutely no way you can do that, because there are so many causes of cancer. The natural incidence of cancer in the United States is about 40–45%. Natural incidence. So how are you going to say that this one CT gave you cancer when you have a 45% chance of getting naturally cancer, right? There's a very high incidence rate. So that's the difficulty. You would have to follow at least 2 million people over a long period of time, statistical significance that the cancer is from a CT. I mean, there's these papers that come out, I'm sorry, but they irritate me because it makes no sense to me, right? They're being very dramatic and they're being alarmist and they're scaring the population that CTs are causing cancer. It's just not true. Look at all the benefit that CT is doing for our patients. I mean, ask any radiologist, ask a physicist, ask a technologist. The benefit that we bring to our patients is far less any risk from the radiation rates.
Okay, thank you. We have a few questions from our online audience. One here, I'm a PhD research student from University of Petronas, Asia. My research is applying deep learning models to LDC images. My questions are, why does edges and lesions have the same intensity level in low contrast region of CT as cited by many journals? And do we differentiate between them?
Can you ask them to email us and for more clarity and background, because it's tough to understand the question?
Okay, then I think for the online audience, we will provide an email.
Yeah.
We'll just be attended to.
Yeah, more clarity on that last question because I haven't either of us understood what is happening.
Okay, just for that question. And then the second question is, what are the current data sets for low dose CT? Current data set. Again, we need clarity on that. So let me just jump to another question. Given the limited access to advanced imaging infrastructure and AI tools in Nigeria, how can researchers, medical physicists, locally begin to explore AI-driven dose optimization?
Very good question. Yeah, so I think physicists in Nigeria, and I think actually applies probably to a lot of physicists in the world, you can start first of all by educating yourself on AI through organizations like American Association of Physicists in Medicine, American College of Radiology. There are a lot of educational tutorials online. The AAPM is in the process of developing AI curriculum for physicists specifically. So that's something you can look at and keep an eye on. In terms of having algorithms, I think there are a lot of free algorithms available online as well. But I think to actually do something on a facility level, you probably have to buy an algorithm. I think starting by looking at the literature, what's being used, try to collaborate with other institutions might be the way to go, and some of these resources I mentioned.
Okay.
Also, we do a lot of in-house analysis of our dose, just from our, that come from our CT scanners. And I do a lot of the analysis there. And to be frank, I use AI and ChatGPT to write a lot of the code, or at least start writing the code to do that analysis. And so if you have a computer, you know, there are so many tools to just basically prompt AI to help you with your analysis. Don't be afraid, yeah.
All right, then we have, as a medical physics student, should I be worried about radiation doses while carrying out CT procedures? So the answer is yes. All right, then I think that's enough questions for now. So thank you very much. A round of applause for our presenters. We'll have a vote of thanks by the Dean of Faculty of Physical Sciences, Professor Ahmadu.
Chairman, the occasion. So I do not have the head of the Department of Physics, and everyone here present. Our public speakers, Mr. Joseph, Richard, and Prof. I'll like to start by welcoming you and congratulating you for giving a very fantastic session. I am a chemist, and as a chemist, okay, sorry. As a chemist, I think and probably understand 5 to 10%. I know we have interacted with X-rays before, and we still do. I mean, when we do our X-ray diffractions, and I think one thing that I've gained from here, or maybe I need to ask again, I don't know. But one thing I've gained is that I shouldn't be afraid of my X-ray machine. Because we actually, I mean, it's, yeah, we don't of cancer and the rest of them. So I've gained valuable lessons today. I think the interaction was very fantastic. It was energetic, and everybody was actually really participating. I could see a lot of people trying to ask questions, which means that you know, the talk was assimilated well, and wanted to answer more. For a talk like this, I think what we'll be looking at in the future be that we get you know, the Department of Physics and Faculty of Physical Science, maybe you know, a sort of collaboration with your own university, such a way that we'll have a mutual benefit, especially for our own graduate students, PhD students, and MSc students, and even for some of our lecturers who might be willing to get one form of training or other. I think if we can have that worked out, not only the department, but for universities at large. So for Prof. Kalpana and Mr. Joseph, I want to say thank you. You have enriched our presence here for the last 1 hour, 2 hours or so. For the chief host, Professor Ahmadu, I want to say a big thank you for actually providing enabling environment for this to happen. For the Department of Physics, Dr. N. Garba, and I will want to say something before I proceed. The student asked why he could use data from ABUT. That is because he is in. I don't think he answered that question. You are doing your PhD here. For God's sake. So you need. This should be your primary source of data from Shika. So I'm going to hold Dr. N. and Garba responsible. And we'll get him to give you here to come and take data. So Professor Ahmadu, head of the Department of Physics, I want to say a very big thank you. You have enriched our presence and have actually put FSP, Faculty of Physical Sciences, on ABU's up. So for everyone who has attended, I think from Shika, have people from Shika, Prof. The provost is here, from provost of College of Medicine, and the HOD of radiology. I want to thank you for our gathering today. For every other person who attended, thank you, and I wish you safe journey out to the various destinations. Thank you, Prof. Thank you, Mr.
Thank you very much. Thank you for the vote of thanks. We'll have closing remarks by the head of the Department of Physics, Professor Ahmadu. Closing remarks.
Thank you very much. Thank you. All protocols duly observed. Let me start by congratulating the Applied Radiation and Physics Research Group of the Department of Physics, led by Professor Rabiu Nasru. I also wish to congratulate one of our staff, Dr. Nuruddin Nasru Garba, for initiating the project and winning the grant. The project is actually ongoing in the Department of Physics, Ahmadu Bello University, Zaria. I also wish to appreciate the American Association of Physicists in Medicine Global Research and Mentorship Program for their effort to strengthen global collaboration in medical physics. I'm hoping for more collaborations between GRE, MP, and the Physics Department, Ahmadu Bello University. Special thanks go to Professor Kamal Kabana and Mr. Zashab Wishot for inspecting the project and delivering the lectures in computed tomography and the role of physicists in AI governance. Finally, I wish all those who attend this memorable occasion a safe journey back to your various destinations. Thank you.
Thank you very much. The barcode displayed here, you could scan to follow the YouTube channel where, of course, we live streamed this event. You could follow the videos and for further clarification. And of course, it's to be done in ABU that's posted on the YouTube channel. Can we take 1 minute to have individual prayers? To close in prayer, please. Thank you very much. Wish each and every one of us to safe journey back to respective destinations.